Hello.
Morning.
Morning. Hello, Vidhi. Can't hear your audio. Yeah, I don't know. Probably have to use the chat. Yeah, there we go. All right.
Yeah, I heard something, but it definitely wasn't a voice. So
All right. So, why don't we get started? So, usually what we do is we start with updates or set of updates for the lab. So, on Monday we had the DevoWorm meeting. That was meeting number 26. We talked about a number of different things in the meeting. We talked about sort of the evolution of intelligent brains, and we had a conversation there. We also talked about peptide modeling, and we talked about the origins of EvoDevo. If you go to the YouTube channel for DevoWorm, you'll see the full meeting there. And so that's quite interesting. Then on Wednesday started the BICA conference, and I put in Cognition Futures. I put a link to the YouTube archive, and I'll talk about that in a little bit. So BICA is biologically inspired cognitive architectures. And it's this meeting that we've been participating in since about 2021. And we have, I think this is going to be the 5th presentation that I've given there. We've done a number of different covered a number of interesting topics that we've been working on this year, and in 2023 we talked about super performance, and then in 2021 and 2022 we did things with the MetaBrain platform that we've done research on in the lab. And I can't remember what we did in 2024. I was trying to remember this morning, but I couldn't come up with it. So we have a number of things I think to follow up on at this point. But anyways, I gave the talk on super performance. It was yesterday. They have their talks on YouTube, and it's still going on. It's supposed to end today. And it's a really interesting conference. It's kind of like AI, but it's not the AI that you usually see from the big corporations. It has this sort of legacy component where, it's kind of a mixture of GoFi and neurosymbolic models and modern AI platforms, like people talk about large language models and transformers, but it's these cognitive architectures which try to approximate cognition for robots and other things. So I'll talk about that in a minute in a little bit more depth, and I'll try to put together kind of a summary later. I'm not going to do that today because it was a couple days. We've been going through it and digesting it. And then yesterday we had our open source meeting, so that is where we did our GSOC updates. And then we also talked about putting open source projects into production. So what does it take to put an open source product into production? What are the opportunities and pitfalls and all of that? So that's what we've done this week. Looks like Morgan's here. Hello, Morgan.
So I'm Vidhi. Bradley and Morgan already know me. I'm a Google Summer of Code 2025 scholar, and I'm working on the Sustain Hub project right now. So I'm using reinforcement learning and getting about the project.
Yeah.
Okay, pleasure to meet you. I'm actually working on some stuff with training the C. elegans connectome using reinforcement learning. So.
Oh wow, that's interesting.
All right, so now I want to talk a little bit about BICA 2025. I'm going to just give a short overview here and then a longer update later. So this is the website for BICA 2025, bicaai.org, and then BICA AI-2025 is the URL. So it's they had this. Actually, this is incorrect in terms of the physical location, but they had a physical location and then they have a virtual component. I, of course, participated in the virtual component. Okay, so this is the one here. It's physically in Puerto Vallarta, Mexico. So they have people at that physical location, most of the people, and then they have people participating online on Zoom, and it's a mix of the two talks, types of talks, in person and virtual. And so, there are some really interesting talks. This is Alexei Samsonovich, and he does a lot of things in what he calls the Institute for Cyber Intelligence Systems, and also works in the Department of Bioengineering at George Mason University. And usually has some pretty good talks. This one was how to teach BICA speak natural language and understand human mentality. So he kind of considered large language models and how we maybe can we can use those, but can we still use symbolic AI? And BICA is considered an instance of symbolic AI. And he talks about how you can augment large language models with these symbolic BICAs or symbolic AI type BICAs. And so this is, so he says BICAs are unique in their potential ability to replicate higher human cognitive functions, volition, personality, social emotional intelligence, goal reasoning, but require intelligent interfaces and symbol grounding to interact with the real-life social environment. And so large language models can pick up where BICAs leave off, and then BICAs pick up where large language models leave off. This was Ricardo Goodwin. He's from Brazil, and his talk was on the pursuit of understanding consciousness and cognitive architectures. This is another kind of talk where they considered large language models and how BICAs can augment large language models. So this is, again, where we have these cognitive architectures, which are really, very large box and arrows models. And, they do different things that are more symbolic than large language models, and you can combine those. This is Ron Sun. Of course, we know his work. He's worked in this area of cognitive architectures for decades. And, he's a cognitive scientist, so he's approaching us not necessarily as I guess he does do engineering, but also he approaches it more from a cognitive science perspective. And this is rethinking rationality and intelligence in AI through cognitive architecture. So this talk examines the literature on rationality and intelligence in AI systems and delves into a specific approach, the development of a neurosymbolic cognitive architecture. So we've talked about neurosymbolic architectures before. This is where you have like connectionist models or these neural network models that have very limited representational capacity. And then you have symbolic models, which are sort of these GoFi models, which model concepts, which work from sort of tables of symbols and things like that, and then merging those two approaches together. So you have sort of the best of both worlds in that sense. So I think this one's happening today. The discussion covers various forms of rationality, different ideas about intelligence, the nature of human activities, the roles of motivation, and so on. And this is all examined through the lens of the cognitive architecture. So this talk also argues that recent computational models are more sophisticated than often assumed, and they are well equipped to overcome many of the criticisms leveled against AI. So they improve upon the sort of AI that's going on right now in ways that sort of address some of the criticisms of AI's current sort of the contemporary state-of-the-art AIs. This is Sean Kugel, and this is his work focuses on artificial intelligence, cognitive modeling, and neurosymbolic systems. The goal of his research is to understand how natural minds, such as human minds, work and to implement biologically inspired software systems based on the same principles. So this is definitely sort of maybe a more engineering-oriented approach, but it does deal with this idea of mental imagery. So his talk was BICAs for Science, Mental Imagery, Consciousness, and the Nature of Thought. And so talking about software agents based on these kind of BICAs can serve as powerful tools for cognitive science. They offer controllable, inspectable platforms for probing complex psychological questions and testing alternative theoretical hypotheses. But while the synthetic approach to understanding minds holds tremendous promise, it also introduces unique methodological challenges. In this talk, I will explore these opportunities and challenges in the context of my recent attempts to use a BICA to investigate mental imagery and aphantasia. And then just thinking about mental imagery, which is seeing with your mind's eye or hearing your voice, is something that is, it's kind of hard to model. Actually, it's kind of hard to get at with experiments, but it's also hard to model with computational models. So this presents a modeling challenge. How can we reconcile the differences in aphantasics, subjective experiences, with their unaffected task performance? And so fully addressing this question requires modeling both conscious and unconscious mental representations and processes. And the answer to this question is bearing on several long-standing debates, including the functional import of mental imagery, the nature of internal representations and processes, and the role of consciousness in producing overt behaviors. And then there were some other talk. This last talk, these were all the keynotes. So this last talk was by Vasilis Kabarlasos, and this talk was human-friendly artificial intelligence enabled with a lattice computing paradigm. And so this kind of talks about conventional deep learning architectures, and then this alternative architecture, which is what he calls lattice computing. So that's pretty mathematically detailed. So that was some of the keynotes. Like I said, I'll go over some of the talks and things later. But and so this is the YouTube channel here. This is what is it called? Senvestav Oficial. It's from the institute that's hosting BICA. So usually it's hosted somewhere at some university. They often host it in Mexico. There's a group, I guess, in Guadalajara that does a lot of work on BICAs, and they hosted this in 2022, I believe, as well. So they have their channel. They have the BICA sessions, and then they have other content on here, which is kind of interesting, but it's in Spanish, so if you don't understand Spanish, the BICA sessions are mostly in English. Okay, so Jesse's not here today, but this would be of interest to Jesse because he posted a lot about this in the Cognition Futures channel of the Slack. I think he attended these meetings, but this is another overview of one of these BI complexity talks. Thinking about like sort of following up on some of the topics that they talked about in the session and kind of giving our own opinions about it. So this is, let's see. So the BI complexity group is this discussion group. They meet online, I think bi-weekly, and they always cover a paper. So they've covered papers from the history of cybernetics, the history of computing, And what I understand, they're kind of building this sort of body of knowledge. You're trying to bring together people interested in these topics and trying to sort of bring insight out of them from a modern perspective. So we've talked about the cybernetics paper. We talked about the Warren Weaver paper. I think it was last week or the week before. This one is a paper by Alan Turing, and this is Computing Machinery and Intelligence. So we're going to be talking about, or they talked about this paper. We're going to be referencing this paper, and it's a paper that was published in the journal Mind in 1950. So we have now 75 years of insight into this work. So everything he talks about in this work is sort of 75 years old. And so we have answers to some of these things. We have perspective on these things. But can we bring that to bear, from what we know now? So this is one image that they talked about. This was actually from the discussion group. So Jesse posted a bunch of slides in the Slack, and he didn't really annotate them, but these are things that they talked about. So this is, I think, Science post 1950. They've divided it into three things. There's nature, which is N, and that's natural processes and phenomena. There's the simulant, which is an abstract formal symbolic model of physics properties of N, or T sub N, and this is materially computed. So for example, nature, something that happens in the world. You can simulate nature in a computer. You can use a circuit or an electrical circuit, and that's kind of how we've approached computation post 1950. So we can take a natural system, we can simulate it on a von Neumann architecture. We have other architectures, but that's the one that we've kind of developed the most over that period of time. So we can simulate nature, but we can also replicate nature. And so this is, whereas a simulant is the abstract formal symbolic model of physical properties, a replicant is an abstract material model that retains the essential natural physics of N. So this is not computation necessarily. This is where you can build a model, a material model, that simulates N. So you can have, you could have, of course, a physical model. Like I could have a physical model of a horse, and it could have a flowing mane, and the mane could be very lifelike, and the horse could, make noises and move. And so those are all things that are replicants because they're not really the natural phenomenon, but they try to model it as closely as possible. And so there are these three divisions of science. We use replicants, simulants, and we do that to study nature. So this is the invitation. So this is they cover this Turing paper from 1950. That's their Zoom link. And so this is a comment from Kevin Mitchell, which was, I guess, in the chat, and Jesse took a picture of it here. The question is whether computational functionalism actually holds or not. It's an assumption that thought equals computation. So what this refers to is this discussion we've been having over probably several years now in the group, which is that when we talk about computation, is computation sort of analogous to something in biology, or is it analogous to thought, or is it something else? And if we think about simulating a natural process, can we use computation to model that process? Do we capture the full process? And a more radical view of that is that natural process computation? So if we go to, say, like a forest fire or a brain or something like that, is there a computational structure there that we could replicate, say, on a von Neumann architecture or some other place, and have a one-to-one correspondence between the two. And so this, we talked about things like natural computation, and then, of course, Church-Turing had something to say about that. Church-Turing-Deutsch, which were two theses advanced that kind of argue that, there is an equivalent computational system for any natural system. And so, but this is still an open question. Is computational functionalism suitable for every type of system in the world? And that has implications for when we study systems in nature. Can we really kind of accurately simulate them? Can we simulate every possible state that they're in? Or is this just kind of an exercise in approximation, and it's not really that, we should just take it with a grain of salt? Okay, Paul.
Sorry to interrupt you. The Church-Turing hypothesis specifically had to deal with computation on natural numbers as opposed to natural simulations, and I just wanted to. Distinction.
This is like kind of leading from some of the things we talked about in the past, but yeah.
I think sometimes computational biologists you guys sometimes really focus on simulating everything. The question is, well, if we can simulate anything, then can we get a model of computation or cognition that works? And, I believe the answer to that would be yes, but the difficulty often comes from making an abstraction that is adequate enough to still suit our purposes, but is also computationally efficient.
Yeah. Yeah. So, yeah, and a lot of people in the sciences, they kind of also have this other view that, we can't really build computational systems that fully capture a lot of, say, like the biology. And that's like another view that, like, and I think it's fair because, we kind of assume, I think a lot of people assume that we can just kind of make this easy correspondence. And, okay, so, all right, that's that. And then this is a timeline, AI and complexity. This is sort of from 1950. So the Church-Turing thesis was back in the 30s. GP computer was in the middle of the 40s. And then from 1950 on, this is the Turing 1950 paper. This is artificial intelligence, GP computer, and then natural complexity physics gone, which go from 1950 on. I'm not really sure what all this means. I wasn't at the talk, but that's their timeline. This is a general purpose of GP, so general purpose computer, and just showing that kind of what people were thinking about there. So the speakers in this session were Dr. Colin Hales and Peter Kitchener, and they were talking about this. They were kind of giving this overview of the Turing paper at the meeting here. And so this is this figure that we saw Science pre-1950, and this kind of this kind of goes through a little bit more of this. So again, we talked about nature, simulant or emulant, and then replicant. And then nature, of course, occurs naturally without human intervention. And so in N or nature, this if we look at combustion, it involves burning. In the simulant or emulant, of course, we're trying to build an abstract formal symbolic model of physics properties. We have this T sub n, which is manually computed by a human computer. And then T sub n is materially computed bias circuit or electrical model. And so N is not we don't have artificial nature. We then have abstract symbolic chemistry of combustion, which is not burning. So we have this abstract symbolic chemistry, and therefore we don't have an artificial aspect. We don't have this artificial nature. We have something that approximates it. But then the replicant, we of course have a material model, and then artificial N would not occur were it not for human intervention. So we have burning, but we also have this artificial system that can simulate nature. So this was the screenshot of the no face palms this week. This is the screenshot of the session. So let's look at what was going on in the chat when they were talking about this. Paul Middlebrooks, who leads these talks, had some sort of figure. It looks interesting, but I can't zoom in enough to see what it is. Let me see if I can get to it. Yeah, I can't see what it is, but that's in any case. This person here said, "What is natural complexity physics?" And then also says, "Okay, so basically getting past the fluff of biocomplexity to algorithms, symbolic computation based on simple ingredients, and see how far we go from there." And then Jessie said, "Ooh," she does. "So this fits real well with cognitive science as a computationally centered medium to center all manner of what a mind is doing." Okay, so that's that slide. This slide talks about distorted science, the legacy of Turing 1950. So this is again considering nature, considering the simulant, and then considering the replicant. And this is kind of talking, this is Colin's take on it, Colin Hale's take on it. So we have nature, which is the brain, N equals the brain. The simulant, which is AI, it's not an artificial brain. All N physics gone, so the physics of the brain are not in the simulant. And then that means that there's never been a T sub N simulant that can become nature N. And then there's the replicant, which does not exist. We don't have an artificial brain that compares with, like, say, what we've done with simulating brain-like processes. And then the essential N physics are retained. So the replicant, again, is this physical model where we could physically emulate, say, the brain or replicate the brain. It wouldn't necessarily have all the properties of the brain. It would be some sort of abstraction. It would indeed be an artificial brain. And they say replicant does not exist, but we've been talking about organoids for a while, and they're not really, of course, replicants of the brain, but a lot of the neural organoids, they do replicate parts of the brain. They do replicate features of the brain. So organoids might be considered a replicant. And so you retain the essential physics in a neural organoid. It's an artificial brain, but it isn't the brain itself. It just has these properties. It has the physical properties of the brain. But it's not a simulant where you're simulating things that are going on in the brain. But the simulation doesn't have physics. It's not an artificial brain. And it can't become nature itself. That's kind of the idea. And then Colin notes, there is a major category error in the use of material simulants that has misled the science. Namely, prediction of voltage by neuromorphic electrical equivalent circuit models does not contact the physics that creates the voltage in brains. EM fields do that, so electromagnetic fields. So this is, again, kind of hashing out these differences between, say, like taking the brain, simulating the brain, and then replicating the brain, and how we might use that in scientific inquiry. This is getting deep into like kind of philosophy of science and things like that. And we'll get into the paper. It'll maybe kind of highlight some of these things that are going on there. So they had this in the comments here. They were talking about material replicants and some of the sort of the philosophical consequences of that. And then Mohammed Ansari here says, is that what Searle was arguing with his Chinese room problem, that we're not modeling the physics of intelligence, but only simulating its syntax with UTM? And then this is a picture of the, I think of the, this is opening Turing's black box. And this is sort of a picture of the Chinese room. And this is, of course, a thought experiment in cognitive science where someone takes a slip of paper and they put it into a box. Maybe the slip of paper has a question or it has like a phrase on it. And then it gets slipped into the box. And then they get an answer out of the box, which is an answer to the question, or maybe it's a translation into another language. And the question is, in this black box, does this process, is there, like, say, a little person in there that's doing the translation, or is it just done at random and it happens to get the right answer? And so that's the sort of the Chinese room problem. And you could update it for sort of thinking more broadly about understanding in technological systems. We had a thing in the chat here. Oh, yeah, I'm probably just, okay, I don't know. Yeah, I might be cutting out a bit, but okay. Yeah, I might be having a little bit of a difficulty with the instance here of Jitsi.
Yeah, I can hear you fine now, but
Okay.
You're cutting in and out for a bit.
All right. And then this, Sean Mannion says, worth noting that 1950 to 1956 included several Macy meetings, ratio club meetings, where Turing first presented this paper in December 1950, and the Shannon McCarthy edited Automata Studies, among other lesser-known events relating to these areas. So this was all part of, at the same time, they're talking about general-purpose computers and simulants and replicants. They're also talking about cybernetics and the legacy of cybernetics and how cybernetics kind of thinks about the brain and thinks about modeling. Okay, so that we talked about the Macy meetings. We've talked about Ratio Club. The Ratio Club, of course, is where they met. This is, I think, a club in London where a lot of people met to talk about sort of the new era of computing, and then they came up with cybernetics as a means to sort of view the world through this computational lens or through this sort of mathematical lens. And there were a lot of ideas in cybernetics that, well, some of them were flushed out. Not all of them were fleshed out, and so they ended up, kind of being half developed, and then people kind of forgot about cybernetics. And so we actually have a group in the lab that we're kind of revisiting those issues and thinking about them in a modern way. Of course, the Macy meetings were these more formal meetings where they thought about cybernetics, and they brought people from a wider set of disciplines to kind of consider how cybernetics could be applied to their field. And again, this is another thing that never really gelled into a robust field, but still has a lot of things to teach us about, how to think about these kinds of problems. Okay, so why don't we get into the paper? Actually, we talk about this first. So this is sort of the follow-up from this meeting this week. So this week I got an email from the email list, and it's in the last discussion, Colin introduced his thoughts on how Turing led to a historically backwards way of trying to understand/explain things. And so what they're going to do this week is talk about sort of a more detailed set of principles. And so that's kind of thing for this coming week. So I don't know what they're going to talk about this week necessarily, but sometimes these discussions go off in different directions. So Jesse posted this in the Slack, and I don't know what necessarily the context of this was, but this kind of is something he found interesting. So I incur and I hear you. This must have been some discussion in the session. There's an interesting set of meetings called the Macy meetings that took place of the cyberneticists in the U.S. Warren McCullough was kind of the chair of all of those. So this is from McCullough Pitts. And he wrote a letter, and I posted in the chat earlier, like a list of that he wrote a letter to everyone who's coming to the 10th and last one. So this is the 10th and last Macy meeting, basically saying we failed and saying, and you know what it means in our own eyes, we stand convicted of gross ignorance and worse, theoretical incompetence. This is, of course, the chair of the Macy meetings, and this is referring to the final Macy meeting. I don't know the year for that. That was the 10th Macy meeting, so it was probably in the late 50s, early 60s. And so, but basically, when you have your meeting and they send out an email, or at the time, I guess a letter, saying you failed and you don't understand what you're doing and you're pretty incompetent, that's not a good sign. But I don't know. Maybe that was just kind of built out of frustration. But anyways, that's kind of where these Macy meetings ended. And maybe that's what it is. Maybe it is a lot of frustration. Maybe the problems were too hard and intractable. And of course, remember, they were thinking about computation and they were thinking about modeling, but they didn't have the tools of the modern era. So it's like maybe they were ahead of their time in a lot of ways. And this is the last of probably one of the most innovative interdisciplinary meetings ever. So it was a pretty interdisciplinary set of meetings. They talked about a lot of things, but again, they left a lot of things hanging out there. And then, of course, Dartmouth narrowed the aperture to just engineering deliberately because McCarthy hated the cybernetic stuff. McCarthy is John McCarthy, who was an AI researcher. And they basically, this is something that happened in the history of cybernetics. Kind of the reason why maybe cybernetics got left in the dust is that there were a lot of times when you have interdisciplinary groups, there's this initial interest in being interdisciplinary, but oftentimes people or personalities will prevail or intervene, and they have their own perspective on things, and they take it in a certain direction. And then when you take a multidisciplinary group in a certain direction, you fail because you're sort of abandoning your original goals. So it's interesting that Dartmouth was the host of a lot of these meetings, and they just basically turned this into an engineering only thing. And this is where, again, they had people from all over, from social sciences, natural sciences, etc. And this is where things kind of just collapse down into engineering. And we've pursued that one way, and computing power has made it possible to do amazing things, even though we went, only symbolic works. So this is interesting because at the time they maybe considered some of the data-driven approaches, and because maybe the state of the technology or something, they considered symbolic models to be superior or the only thing that would work. And so that's interesting because today we don't think about just purely symbolic models. We think about data-driven models, and we want to train our models with more and more data. And, we kind of pay lip service to neurosymbolic models, but the symbolic aspect maybe is viewed as a failure. And so this is maybe what they're lamenting, which is symbolic models are not the way to go. And, this is, of course, corresponds with the AI summers and winters. So, of course, we had these AI summers where there was a lot of extraordinary enthusiasm around different AI models that came about. So we had an AI summer around symbolic models. We had an AI summer around purely connectionist models. And then as those models, the shortcomings were sort of discovered, we had these AI winters which followed, which was where the certain people overcorrected and abandoned those models and funding dried up. And then people would try something new later, which would lead to a new summer and then another winter. And so we've talked about AI summers and winters as this sort of, fluctuating aspect of the field. And so, again, this is where they kind of maybe over-promised in terms of symbolic models, and it wasn't delivered. And then it says, and then, oh wait, only connection this stuff, which means they also, I guess what they're saying here is that maybe it was a camp of people that wanted to use symbolic models and were arguing that those were the way to go and you can't necessarily use any other way. And there were also people who were early connectionists who wanted to go in that direction. So it happens a lot of times in interdisciplinary groups where there's two separate competing camps and it becomes untenable to satisfy them both. And indeed, now no one wants to bring those two pieces together. And so now, there are people doing neurosymbolic work, but then the question is, what is the best balance of both of those types of models? So we've fractured the engineering into connectionist and neurosymbolic. We've forgotten all the expert system stuff that was done in Japan before their economy collapsed in the 1980s. This is, I think, Paul Middlebrooks talking about the modern perspective. The Japanese were doing some excellent work, or I guess they still do, on neurosymbolic and expert systems work. So they were doing like neurofuzzy and some other things back in the 80s. And this was, of course, where they were doing these amazing things with robots back then as well. But this is, again, there are all sorts of different kind of research directions that were pursued by, and then kind of left on the floor. So these things haven't even been integrated into the engineering, much less the cognitive science integration, much less the neuroscience integration. The psychology integration, the mathematics and philosophy to underlie it all. So, a lot of the things like what the Japanese were doing with, say, like fuzzy systems and neurofuzzy and things like that, that was purely an engineering kind of approach. They, kind of use those as applications, but then thinking about the cognitive science aspect, the neuroscience aspect, and these other fields. This is where a lot of the work that we've done with, in fact, a lot of the work that's been done with AI since the Ratio Club stopped, or the NACI conferences stopped, is, there's a lack of this sort of integration into other fields, at least in a formal way. We've broken into 1,000 little pieces, and we don't yet have a way to bring them all together. We need a vendor style, bring them together and put them in the glove, I think, at some point. But I totally agree with that. We've been looking at tiny little pieces all over the place, more and more minuscule over the last 75 years, because we don't have any theoretical way of putting them together. So this is sort of a lament about kind of the state of how we think about these technical problems and then how we bring them to other fields. And there is a symbiosis there, which is missing when you're missing that big interdisciplinary cast of things. So I guess it's something that came up during the meeting. So let's go to the paper then. This is Computing Machinery and Intelligence from 1950. And so this is the first part here. I guess he writes it in these parts. The first is the imitation game. And so this is, I propose to consider the question, can machines think? They should begin with definitions of the meaning of the terms machine and think. The definitions might be framed so as to reflect, so far as possible, the normal use of the words, but this attitude is dangerous. If the meaning of the words machine and think are to be found by examining how they are commonly used, it is difficult to escape the conclusion that the meaning and the answer to the question, can machines think, is to be sought in a statistical survey such as a Gallup poll. But this is absurd. Instead of attempting such a definition, I shall replace the question by another, which is closely related. The new form of the problem can be described in terms of a game, which we call the imitation game. It is played with 3 people, a man A, a woman B, and an interrogator C. The interrogator stays in a room apart from the other 2. The object of the game for the interrogator is to determine which of the other 2 is the man and which is the woman. So it's just basically like asking questions and each trying to deduce their identity and then, not having that information in advance. So the interrogator knows them by labels X and Y, and at the end of the game, they say either X is A or Y is B. So you get these 2 agents. You don't know their true identity. You ask them questions, and then at the end of this game, you try to ascribe the correct label. So this sounds a lot like maybe supervised learning that we would do today, where we have this information, and then we try to sort of, I guess maybe semi-supervised learning, because you have this information, and then you try to assign labels with some degree of confidence. And so this kind of goes over the imitation game. And then number 2 is critique of the new problem. So as well as asking, what is the answer to this new form of the question? One may ask, is this new question a worthy one to investigate? This latter question we investigate without further ado, thereby cutting short an infinite regress. The new problem has the advantage of drawing a fairly sharp line between the physical and intellectual capacities. No engineer or chemist claims to be able to produce a material which is indistinguishable from human skin. So this is where they're getting into this this replicant aspect. We talked about the simulant and the replicant. So this is where they're kind of getting at this this distinction. It is possible that at some time this might be done, but even supposing the invention were available, we should feel there's little point in trying to make a thinking machine more human by dressing it up in such artificial flesh. So he's making this point that you could make, like if you wanted to simulate the brain, you could build a physical model of the brain. You could have the physical properties of the brain, but that doesn't make it any more of a thinking machine. And, so you don't necessarily maybe need that. The form in which we have set the problem reflects the fact and the condition which prevents the interrogator from seeing or touching the other competitors or hearing their voices. So basically, we don't need the replicant to make a correct determination of their label or their identity. We just need the information, and that's all that matters. So we can use a simulant to do the same thing. Some other advantages of the criterion may show up by specimen questions or answers. So again, you do this question and answering, and you're getting the information that you need, and you can basically accomplish the task without building a physical model. This may seem a little silly and trivial today, but if you think about how people approached this before 1950, they didn't have people didn't have the frame of reference of a digital computer like we do today. It was like people would build automaton, and they would, have all sorts of different ways of kind of simulating living systems. So what I mean by automaton are these little physical models. You'd have little robots that you'd wind them up and they'd walk, and they were physical instantiations of something. Or you'd have if you remember from the movie Big, Zoltar, which was this, thing. It was a model of like this person who would give out answers to questions. It was a mechanical system that would stamp out these answers to questions, and it was, so this was kind of the frame of reference people had before 1950. So that was I think that was maybe kind of the context here. The question and answer method seems to be suitable for introducing almost any one of the fields of human endeavor that we wish to include. We do not wish to penalize the machine for its inability to shine in beauty competitions, nor to penalize a man for losing in a race against an airplane. The conditions of our game make these disabilities irrelevant. The witness can brag if they consider it advisable as much as they please about their charms, strength, or heroism, but the interrogator cannot demand practical demonstrations. So all the interrogator has to work with, instead of some practical demonstration, is just these questions, and they have no connection to any physical attributes like voice or anything else. It's just kind of the answers to the questions. The game may perhaps be criticized on the grounds that the odds are weighted too heavily against the machine. So the machine gets information, but it doesn't get all the nonverbal information that we usually get in a conversation. It gets just the information as natural language. And of course, you could also do this with, say, binary or something else that would just give the information. It would be compressed in a way that, you could distinguish between different answers to different questions and then make the proper label. May not machines carry out something which ought to be described as thinking, but which is very different from what a man does? This objection is a very strong one, but at least we can say if, nevertheless, a machine can be constructed to play the imitation game satisfactorily, we need not be troubled by this objection. So that's kind of the frame of what this imitation game, or what it means. And then talking about the machines concerned in the game, the question will not quite be definite until we have specified what we mean by the word machine. It is natural that we should wish to permit every kind of engineering technique to be used in our machines. We would also wish to allow the possibility that an engineer or team of engineers may construct a machine which works, but its manner of operation cannot be satisfactorily described by its constructors because they have applied a method which is largely experimental. Finally, we wish to exclude from the machines men born in the usual manner. It is difficult to frame the definition so as to satisfy these three conditions. So we have, the three conditions are where we want to have every kind of engineering technique to be used. We want to be able to construct a machine where the manner of operation cannot be satisfactorily described by its constructors. So we don't know how it was, how it works. We want to try every type of technique that we can. And then we want to exclude from machines people. So we don't want people behind the scenes. So if we go back to the Chinese room, we want a machine that isn't aided by humans, that works by a variety of mechanisms, and something that we can't necessarily interpret, or it is not interpretable. It is difficult to frame the definition so as to satisfy these three conditions, so we can't really do this in real life. One might, for instance, insist that the team of engineers should be all of one sex, but this would not really be satisfactory, or it is probably possible to, this is not. To do this, so it would be a feat of biological technique. Okay. Okay, so let's see. Okay, so that's a little bit about, the machines that we're using, how we can think about building these machines. we want to construct a thinking machine, but we need to sort of consider these different ways of constructing the machine. We are the most ready to do so in view of the fact that the present interest in thinking machines has been aroused by a particular kind of machine, usually called an electronic computer or digital computer. Following this suggestion, we only permit digital computers to take part in our game. So what he's saying here is that we have these different constraints for building a machine for this game, but we're only kind of using digital computers. We could use things beyond digital computers, but this is not, we can think outside of this box. And then he gets into digital computers and what those are, sort of the basic components that you have in a digital computer and how information is processed, and then walking through some more technical details and some objections to this approach. So that's the paper. So that was their meeting, and I guess they went through the history of it, and they're going to talk about more this week. But I want to go through that because Jesse was very excited about it in the Slack. And I don't know if he's not here today, but yeah. So that's a historical note about thinking machines and about the different types of computation and things like that. Any comments or questions on that?
I unfortunately for you have a ton of comments.
Oh, sorry.
And I might incite your ire.
Okay.
I'm going to start with the 1950 Turing paper, which, I mean, it's probably one of his most popular papers.
Yeah.
Probably because it's the most accessible to laymen. It was published in 1950, towards the end of the career. It was published in I think in a philosophical or psychological journal or something along those lines.
Yeah.
However, I don't think that the imitation game that Alan Turing proposes is quite relevant to our work. So his main argument was we do not have a good definition for two things. One is thought. The other is consciousness. So he proposes this test, and essentially the test is, okay, can some outside observer, they write things on a piece of paper, they put it into a box, and the box spits out an answer. Can they discern whether the thing in the box is a human or a computer? Can they tell the difference? But the whole thing about thought or cognition having no set definition, these are actually very important things to what we are trying to do in cognitive science. Turing as an engineer throws that out, and I have a lot of respect for Turing's other work. Like the Turing machine paper is great, but this is probably my least favorite one of his papers. I want to jump from this to the Slack message that Jesse wrote. It's very pessimistic. And I will admit that I do not have the best knowledge of the history of cybernetic systems. However, I can speak to neurosymbolic computing because it is something that I follow. It is something that I've been doing research in, although no publications on it yet. But there have been very, very significant advances in neurosymbolic computing. One of them was DreamCoder, where essentially the initial challenge is to use is to essentially create a program that can solve or create an AI that can solve problems through generating programs. What DreamCoder is able to do is it's also able to dream up problems and then create solutions to those problems. And that was published back in 2021. It was a pretty significant paper in neurosymbolic computing. So it's the natural course of research for certain fields to sort of be dropped to the wayside. That was the case with AI. You mentioned the AI winters. One of the reasons why it was dropped to the wayside was because there is this paper published, and basically it said that we would never be able to have multi-layered perceptrons, which as the perceptron was formulated, that was true, because the perceptron had like literally a digital activation function. So there is no way to take a derivative of that. But that paper saying creating stacking perceptrons on top of each other was impossible, effectively killed AI research. And Geoffrey Hinton, who won the Nobel Prize for physics for research related to AI, that's a whole separate discussion. Like, should have he won the Nobel Prize in physics? Not going to get into that. But he actually had an argument with somebody, I think in the 70s or 80s, and they were arguing that what he was trying to do was impossible. Right? By changing the activation function, we like that essentially gave a rebirth to machine learning and deep learning in the 80s and 90s, and here we are today. Going back to the Turing paper, there is an arXiv paper that was posted on March 2025. I'm going to put that in the chat. And it deals with the Turing paper, and the title is literally "Large Language Models Pass the Turing Test," meaning that LLM, and it shows basically, I think ChatGPT 4.5 or something, it might have been 4.0 mini, can trick a user about 75% of the time in thinking that it's a human. Here's the question I have for the people in this group: is that particularly relevant for us? And I'm throwing myself in this category, even though I'm an AI researcher, not like a computational neuroscientist. But as a computational neuroscientist, is that particularly useful to us? Not really, because it's investigating a different problem than we are trying to solve. We're trying to create a computational basis for cognition. So I'm sorry for ranting so long. It's just something that I'm very passionate about. We don't necessarily have to build like a model from the ground up, because the question is, okay, where do we start? We don't necessarily have to start at like the chemical level or the physical level, or even modeling, quarks, but we are trying to model cognition to a certain point. So it is actually very important for us to sort of define consciousness and define thought, and think about what our objectives and goals are. So I will end my rant there and apologize deeply to the group.
Oh no, this is great. Thank you. Yeah, I mean, I agree with a lot of like what you said in terms of, the paper that they covered here was, thank you for the DreamCoder paper. Yeah. This wasn't Turing's most insightful paper. And, a lot of the aspects of the AI summers and winters, I think part of that was because people kind of had, I like to kind of describe it as like hype cycles in business and innovation, where like people get their hands on something and they try things, and there's a lot of sort of excitement around it, and then they can't figure out, how, like they get some of the technical details down, and then they don't get all the technical details down, and they consider something to be a failure, so they kind of put it by the wayside. And then, of course, as you said, with multi-layer perceptrons, that actually was a solvable problem with later innovation, with later research. So it actually, but yeah, this is, and then in terms of like thinking about, like this is the paper, Large Language Models Pass the Turing Test. This is an interesting paper. So this is where They evaluated 4 systems: Eliza, GPT 4.0 or 4.0, Llama 3.1, and GPT 4.5, and 2 randomized controlled and pre-registered Turing tests on independent populations. Participants had 5-minute conversations simultaneously with another human participant in one of those systems before judging which partner they thought was human. So they talked to a human, they talked to a language model, and then they had to make that distinction. When prompted to adopt a human-like persona, GPT 4.5 was judged to be human 73% of the time, significantly more often than interrogators selected the real human participant. So this is where there's this distinction to be made. And, it's interesting to note, like, how people were making that distinction. I mean, it may have been not always in the same way, but nevertheless, they were able, they basically couldn't make that proper judgment or that category. Llama 3.1 with the same prompt was judged to be human 56% of the time, while baseline models Eliza and GPT 4.0 achieved win rates significantly below chance, 23 and 21% respectively. The results constitute the first empirical evidence that any artificial system passes a standard 3-party Turing test. The results have implications for debates about what kind of intelligence is exhibited by large language models. And so that's kind of that. Okay, so we had a comment in the, Vidhi asked, BNY uses Eliza, right? Is this BNY is what?
Like BNY is the Bank of New York. I think they have collaborated with OpenAI and they are using Eliza right now, like the tool, the LLM in the company.
Yeah. So that's interesting. Yeah, that's kind of the imitation game in the modern context, but in terms of thinking about language models and human conversation. So I'm not sure kind of where, because we've talked about some of the ways that they've applied reasoning models, and so like large language models can produce linguistic output, but then there are these reasoning models that have been built on top of large language models, usually like reinforcement learning models, where they try to refine the output and allow the large language models to reason. And that's kind of, I don't know what level they were they having like an informal conversation, or were they asking about specific types of problems? How do you solve this problem? How do you solve that problem? But it's interesting that the different language models got different degrees of correctness, or people got.
It's worth mentioning that reasoning process, that isn't the RL portion, which I'm blanking on the name of that, but generally that's due to chain of thought reasoning.
Yeah, chain of
thought. The RL portion is when ChatGPT prompts you which answer is better, and there's a whole RL process that they use to fine tune their models, which is actually very effective.
Yeah. Okay, and then why don't we go to the other paper that you posted in here, the DreamCoder. So this is DreamCoder. This is this neurosymbolic paper, bootstrapping inductive program synthesis of wake-sleep library learning. So this is actually Josh Tenenbaum is on this paper. So this is, we present a system for inductive program synthesis called DreamCoder. So they're doing program synthesis, which inputs a corpus of synthesis problems, each specified by one or a few examples, and automatically derives a library of program components and a neural search policy that can be used to effectively solve other similar synthesis problems. The library and search policy bootstrap each other iteratively through a variant of wake-sleep approximate Bayesian learning. So they have these wake-sleep cycles that approximate Bayesian learning. A new refactoring algorithm based on eGraph matching identifies common subcomponents across synthesized programs, building a progressively deepening library of abstractions, capturing the structure of the input domain. So they evaluate classic program synthesis areas and AI tests such as planning, inverse graphics, and equation discovery. So jointly learning the library and neural search policy leads to solving more problems and solving them more quickly. That's, I don't know if Morgan, because he's interested in program synthesis and things like that, if there's anything to say about that.
I do. I'm just driving right now.
Okay.
But thank you. Or yeah, I'll try to in a bit.
All right. Yeah. Okay. Yeah. So I don't know if we wanted to talk about, wanted to continue on with this line of discussion, or have anything else to say? Okay. Well, yeah, that's interesting stuff, and we'll come back to Morgan later. Okay. Actually, I'm going to talk about this for a while. This is a set of papers where this is kind of moving away a little bit from the AI discussion and talking about something called conservation laws and modeling physics. So, you know, in physics, we have conservation laws, we have thermodynamics. And so we can approach machine learning through incorporating physical principles. We can learn conservation principles using machine learning. And then we can also kind of think about conservation laws as sort of a framework for understanding self-organizing systems. So I'm going to go through these three papers and see what the state of the art is in this area. It's kind of a broad area, and it involves a number of different sorts of approaches and things like that. But, you know, we will learn something more about physics modeling and things like that as we go along. So this first paper is from the arXiv. It's from the condensed matter, soft matter part of the arXiv. And this is a unifying approach to self-organizing systems interacting via conservation laws. So the abstract reads, let me zoom in. We present a unified framework for embedding and analyzing dynamical systems using generalized projection operators rooted in local conservation laws. So in this paper, what they want to do is they want to understand, analyze dynamical systems. They want to embed dynamical systems using a certain type of mathematical framework. By representing physical, biological, and engineered systems as graphs with incidence and cycle matrices, we derive drill projection operators that decompose network fluxes and potentials. So they're using this formalism to represent these kind of physical, biological, and engineered systems. This formalism aligns with principles of non-equilibrium thermodynamics and captures a broad class of systems governed by flux forcing relationships and local constraints. So what they're doing is they're taking this mathematical model and they're capturing a lot of these aspects of physical systems. We extend this approach to collective dynamics through this thing called PREDS, which is projective embedding of dynamical systems. And so this is an embedding of the dynamics of these kinds of systems, which lifts low-dimensional dynamics into high-dimensional space, enabling both replication and recovery of the original dynamics. So what they're doing is they're looking at these kinds of dynamical systems. They take low-dimensional dynamics, they embed them in a high-dimensional space, or they lift them up. They enable the recovery of the original dynamics, which is important. When systems fall within the PREDS class, their collective behavior can be effectively approximated through projection onto a mean field space. So this enables us to be able to approximate these kinds of, the behavior of these kinds of dynamical systems. We demonstrate the versatility of PREDS across diverse domains, including resistive and memristive circuits, adaptive flow networks such as slime molds, elastic string networks, and particle swarms. So these are, I guess these are, you can think of these as computational systems. So what we're doing is we're trying to approximate these dynamics in these different types of computational systems, or these information processing systems, which are not von Neumann computers at all. They're in fact physical or physiobiological systems. And so we have particle swarms, memristive circuits, adaptive flow networks such as slime molds. Of course, there's slime mold computing. There's swarm particle optimization. There are elastic string. You can compute on networks and things like that. Notably, we establish a direct correspondence between PREDS and swarm dynamics. So we can use swarm dynamics as a particular instance of this, revealing new insights into optimization and self-organization. Our results offer a general theoretical foundation for analyzing complex network systems and for designing systems that self-organize through local interactions. Okay, so this is Paul Seidman.
Smart, to distract you.
What was that? Seidman, memristive circuits were one of the main approaches to neuromorphic computing. I'm not sure whether these things have changed since I was last reading in that field. Yeah, this is one of the key technologies in neuromorphic computing. I think it still holds. Yeah, so you're doing a lot of different types of unconventional computing. I mean, unconventional being not typical stuff. So, yeah, so this is, and then this is they have their table of contents here where they kind of go through and talk about some of these kind of physical and biological computational systems, dissipative networks, resistive and memristive circuits, adaptive flow networks and slime molds and elastic spring networks. So this variety of physical kind of systems and being able to replicate dynamics on these. Then they have the PREDS approach here, which they lay out in part 2. They're mapping PREDS to a particle swarm model, and then they do these numerical systems simulations of particle swarms where they kind of show this model in action. And then, of course, they talk about graph theory, network dynamics, and then these different sort of circuit-based dynamics and memristive networks, flow networks, Hookean networks, and projection-based adaptation. I'm not sure what a Hookean network is. It could be something to do with cells. And then particle swarms in particular, where we have things specific to that. So this is kind of talking about how to model conservation laws as part of the dynamics of dynamical systems, and then mapping them to these non-traditional computing paradigms. And so I'm not going to go through the whole paper, but I just wanted to make people aware of this kind of work and how, and there's a lot of technical detail on the paper itself. But basically, they're taking the dynamics of a system, they're putting it into a higher dimensional space, and then they're putting it into these frameworks where you can actually model, or I guess you can play the physics and the dynamics out in these systems. Okay, so that's an interesting paper, and I'm not, I don't have a handle on all the technical details. It'd probably go over our heads, but that's, the way a lot of the, when people are kind of applying physics to computation, typically what happens, at least to me anyways. This is a second paper here, which is from Machine Learning, Science and Technology. Now, this is a different sort of thing. This is beyond dynamics, learning to discover conservation principles. So this is where you're taking data from maybe like a dynamical system, and you're learning or discovering conservation principles from them using a more standard machine learning approach. So this is the abstract here. The discovery of conservation principles is crucial for understanding the fundamental behavior of both classical and quantum physical systems across numerous domains. This paper introduces an innovative method that merges representation learning and topological analysis to explore the topology of conservation law spaces. So this is where, I guess you're learning things like a network topology or sort of the configurational entropy of some system, and you're able to merge that with representation learning. Notably, the robustness of our approach to noise makes it suitable for complex experimental setups, and its aptitude extends to the analysis of quantum systems, as successfully demonstrated in this paper. Okay, we exemplify our method's potential to unearth previously unknown conservation principles and endorse interdisciplinary research through a variety of physical simulations. In conclusion, the work emphasizes the significance of data-driven techniques and deepening our comprehension of the principles governing classical and quantum physical systems. So this is where, we don't really understand fully the conservation laws involved in real-world systems. So if we collect data on them and, analyze them using machine learning, we can maybe discover new principles. And so this kind of talks a little bit about conservation laws and their importance to the physical world. The discovery and application of these principles span various disciplines. In recent years, data-driven techniques have emerged as powerful tools for uncovering previously unknown principles and fostering innovative interdisciplinary research. So their novel method tackles the challenge of revealing hidden conservation laws through the synergistic combination of representation learning and topological analysis. And so they organize their paper in terms of first covering related work. So their previous approaches to the discovery of conservation laws. Then there's a methods description, which details their data-driven algorithm. And then in section 4, they analyze the implications, limitations, and future research of their approach. They do some physical simulations, and then they discuss the implications of that, and then they highlight critical insights and emphasize the potential of this technique in advancing our understanding of conservation laws. So actually, if we go down to section 6, they talk about the limitations. They talk about the comparison. So why don't we talk about the comparison and then the limitations and then some of the broader implications. So glossing over the technical details to get to some of the sort of broader implications here. So in terms of the comparison, on the simple example of the coupled oscillator, so they give an example of a coupled oscillator in one of their experiments. Our approach showed the ability to discover the underlying principles as good as the previous methods. However, we achieved the new previously unmet results for the more complicated systems. More specifically, in the experiment with the oscillating Turing patterns, we showed that the ability of our algorithm to uncover topologically non-trivial shape space, while method proposed by Liu 2022 is only able to represent the same shape space in the higher dimension. So they're doing things with oscillators and Turing patterns, which are, different patterns of, different shapes that emerge from this sort of chemical morphogenesis process. And oscillators, of course, are things that produce oscillations. Those, they're able to compare it with some of the existing methods, and they're able to do this, I think, more effectively, is their point. Furthermore, our algorithm was able to discover the number of conserved quantities in a quantum system, which has not been done by the previous algorithms covered in their review of the contemporary methods. We cannot compare our method to the other approaches solving the same problem because ITIN et al. 2020 do not have open code for their approach, and the method of Liu 2022 has hyperparameters which we cannot tune. So that's fun. It's always fun to have this kind of limitations. But the point is that they do, pretty good job with respect to previous work, and they actually come up with some pretty novel results in comparison. Now, their approach that they propose here has a few limitations. One comes from assumptions about the dynamical system and the data collected from it. So the trajectories of the dynamical system should be ergodic. And even though most of the simpler physical systems are ergodic, non-ergodic systems exist. In fact, most systems in the real world are non-ergodic. Ergodic assumptions are usually, idealized assumptions. So, if you're doing the sort of data-driven approach, you need to be able to deal with non-ergodic systems, which are interesting for discovering, but not available for discovery with our approach. Another aspect of data collection is that all conserved quantities should vary. Moreover, variations of different quantities should have approximately the same magnitude. Otherwise, the algorithm will not detect directions in the shape space C with a small variance, resulting in an underestimated number of conservation laws. So there are some systems that don't have conservation laws, and one example of that is a pendulum with friction. So a pendulum is this weight, on a rod or a string that moves back and forth, and there's friction on that pendulum. So this is a system without a conservation law. And this can, so that sort of systems without conservation laws also cannot be found by our algorithm, since the minimal possible prediction about the number of conservation laws for our algorithms is 1. So sometimes you can't model certain physical systems that don't have conservation laws. In addition, trajectories should be sampled long enough to represent the respective isosurface well. And so this is where we have this sort of abstraction from the physical system to model some of the dynamics. And we need to have trajectories that can be sampled long enough to extract those dynamics. And so, again, when you're obtaining data from physical systems, it's hard to know at what time scale the dynamics emerge. You can have things like coupled oscillators where the temporal dynamics are much longer than, like, say, a simple oscillator or a single oscillator. And so those are things that you need to understand before you try to extract conservation laws. Another limitation comes in the number of trajectories. As we've shown in our examples, if the number of conservation laws in a system is low, is it enough to sample 200 trajectories, even for systems with very complicated shape spaces? And then so the question is, or I guess it is enough to sample that many. So if you know the number of conservation laws that exist in your system, it's, sparse sampling is probably good enough. And so that's kind of what they've found here. However, we expect the required number of trajectories to grow exponentially with respect to the number of conserved quantities, which makes it computationally more expensive to evaluate our model on the systems with high number of conserved quantities. So that's kind of the limitation there, is we don't necessarily know from any given physical system what level of sort of complexity or conservation laws we should expect. So it's kind of hard to do this exercise. We can maybe do this for well-characterized systems well, but we need to characterize our physical system before we can extract laws from And there's this whole literature on finding scientific laws as well. Like there are people who have tried this with different software platforms, or they tried to extract like equations that describe different aspects of a physical system. And this has been like a quest that's been ongoing for decades, where you'll have some algorithm that will extract all these potential equations, and then you try to like evaluate those equations and see which ones best describe the system's dynamics across all manner of different state configurations. So you make that ergodic assumption about the system, and you search for the laws or the equations that fit that assumption. And so that's kind of where we are. So they really kind of made a nice exploration of this. And overall, this work emphasizes the potential of data-driven techniques to advance our understanding of conservation laws. The robustness to noise. Okay, we believe this approach can drive innovations in interdisciplinary collaboration by helping researchers elucidate the core principles that dictate system behavior across numerous domains. Further refinements of this technique could enhance its applicability to even more intricate systems. They don't really give like good application domains, but that's kind of, it's the way these things go sometimes. It's hard to know where to apply them. So this is the last paper here. This talks about Hebbian physics networks, a self-organized and computational architecture based on local physics laws. So they're thinking about this more in terms of how to merge Hebbian learning with physics and learning physics laws. So traditional machine learning approaches in physics rely on global optimization, limiting interpretability, and enforcing physical constraints externally. So this is kind of this approach to machine learning where you're doing global optimization. So they want to kind of break out of that paradigm. So they introduced the Hebbian Physics Network, or HPN, which is a self-organizing computational framework in which learning emerges from local Hebbian updates driven by violations of conservation laws. So whenever conservation laws are violated, it learns those violations and it tries to frame the discovery of conservation laws in that context. Grounded in non-equilibrium thermodynamics and inspired by Prigogine's theory of dissipative structures, HPNs eliminate the need for global loss functions by encoding physical laws directly into the system's local dynamics. So it's kind of working from this principle of dissipative structures and non-equilibrium thermodynamics, which is more applicable to real-world systems, by the way. Residuals, quantified imbalances in continuity, momentum, or energy, serve as thermodynamic signals that drive weight adaptation through generalized Hebbian plasticity. So the network is learning from these different imbalances, different heterogeneities of the dynamics, and it's learning from that. We demonstrate this approach on incompressible fluid flows and continuum diffusion, where physically consistent structures emerge from random initial conditions without supervision. HPNs reframe computation as a residual-driven thermodynamic process, offering an interpretable, scalable, and physically grounded alternative for modeling complex dynamical systems. So this kind of shows this graphic in Figure 1. This is a conceptual lineage of Hebbian physics networks. And so they start with the Hope field network, which is where you start by trying to find the energy minima. And then you have this Boltzmann machine, which is grounded in equilibrium thermodynamics. And then it leads to the Hebbian physics network, which is grounded in non-equilibrium thermodynamics. So it's like you transition between these three types of models. So the Hope field network model convergence to deterministic energy minima. Boltzmann machines incorporate stochastic equilibrium sampling. And then HPNs generalize these approaches to non-equilibrium systems. So kind of like one approach builds on the next approach, leading to this Hebbian physics network. So traditional machine learning methods in physics often depend on global optimization procedures, such as backpropagation. While these techniques are effective, they can be computationally expensive, difficult to interpret, and detached from physical principles. So, we have different optimization procedures, but are they really, modeling physics? Are they really close to the dynamics, or are they just kind of abstracting too much away? We propose a fundamentally different approach, which they call Hebbian physics networks. And this is a classic computational network in which nodes evolve through local, physically interpretable updates without requiring any global loss function. So this is where we don't need a loss function. We just need to make these local updates, and we can build a good model of physics for different types of dynamics. Previous frameworks, including Hope field networks, Boltzmann machines, energy-based models, spiking neural networks, and the free energy principle, which they throw in there, have incorporated notions of locality or thermodynamic grounding. So these are all kind of these kind of physics-inspired models that are also have this neural component, and they try to predict, you can use them to predict the physics of a system. However, they remain fundamentally tied to equilibrium paradigms or global supervision. So you have a lot of these systems that model physics, sort of model them with this equilibrium assumption. And of course, a lot of real-world physics were interested in far from equilibrium or non-equilibrium phenomena. HPNs depart from equilibrium-based or globally optimized frameworks by embedding principles of non-equilibrium thermodynamics directly into the network architecture. And inspired by Prigoghine's theory of dissipative structures, each node encodes a physical variable and evolves by penalizing connections that increase local residuals, such as violations of continuity, energy balance, or phase space conservation. Synaptic weights are updated through a reinterpreted Hebbian rule, reinforces physically consistent interactions while suppressing inconsistent ones with a biologically motivated decay term. And so they kind of talk about this class of conventional physics-informed neural networks, or PINs. And these are models that have been explored recently to sort of model these equilibrium physics. PINs enforce physical laws externally via loss functions, but in contrast to HPNs learn from within, the physics are not added to the network, but rather derive it. The result is a self-organizing, interpretable framework capable of reproducing complex physical dynamics without global optimization or the explicit discretization of partial differential equations. So that is the Hebbian physics networks. So these are three different approaches, very different in the way that they're approaching a problem, different problem domains. Okay, so Paul, he put the links to the papers in the chat. Thank you very much for that. So any comments or questions on that? Okay. So Paul says, Hope field networks were originally conceptualized as a robust way of storing information. Basically, a Hope field network has a set of nodes and are connected by edges. If a value of the node is accidentally erased, it can be reconstructed from the value of the edges. And then Hope field methods are trained by minimizing an energy function. There has to be an unlearning process so that the edges don't just converge to zero. There's something called the Crick-Michelson hypothesis. It basically states that unlearning is related to the reason why we need sleep. Oh yes, the sleep where we consolidate memory by unlearning things, and yeah, it's good. Yeah, there's this unlearning process in Hope field networks, and it's just kind of a way to keep the network from converging. Yeah.
Yeah, hot field networks are no longer taught in ML, and I think that's kind of a mistake. Like we should also cover, restricted Boltzmann machines and hot field networks. I think there's some interesting things there, even if they're not used.
Yeah, I think so too. Yeah, there's a lot of interesting stuff that we can learn from kind of thinking about physical systems. And then this goes back to this discussion of the Turing paper, which, I realize that there's the Turing paper, and then there's this discussion they had in the BI group where they kind of talked about sort of the implications, and they talked about, different ways to think about systems. So you have the simulant and the replicant. And what we're talking about here is maybe a combination of the two, where you have the simulant but also the replicant, because you have physical systems, but you're also looking at the computational representation. It looks like Morgan is ready to go here.
Good morning.
Morning.
I don't know about ready to go. Having my first sip of coffee, so yeah. I mean, whenever I see these, they're super interesting. I'm not. Well, again, I think if I was more of a computer engineer,
Yeah.
as opposed to a more wannabe break-in scientist,
Yeah.
I might get more from these, but it is fascinating in a kind of Levin-esque kind of way to see the diverse forms of computation.
Yeah.
I guess, when I think about the kind of physics laws, or I still think like physics informed neural networks might be more interesting, again, for the kinds of problems that I'm interested in.
Yeah.
Where you've got neuroimaging techniques that you could use some physics constraints in the mathematical modeling, which is like both computationally super efficient as well as potentially providing superior resolution and but that's my practical take. I mean, I love I mean, of course, I always think of Adam Adamansky, although I don't think he does any physical computation kind of work, does he?
No, I think his work is largely on things like slime molds, looking at the computation.
He's more in the unconventional.
Right. Yeah.
Yeah. But I still, I do try to follow the neuromorphic computing, because it does. I think at some point it will maybe be more relevant for the designs of like organoid intelligence, or again, the biological computation.
Right.
But
Yeah.
The not Turing like papers, but the big discussion in computational psychiatry right now is about the different language models and their ability to engage in therapeutic conversations.
Yeah.
And what goes wrong with language models when you ask them, when you constrain them in a therapy patient kind of relationship.
Right.
Basically how they become sociopathic.
Oh, right. We talked about that. Yeah.
Which is it's an interesting it's an interesting problem.
Yeah.
But I just saw like Tom Insel and a couple other people chime in on this most recently.
Yeah.
And I think he's definitely been in Silicon Valley too long.
Yeah.
Like, now with ChatGPT 5 coming out, we should have a serious conversation about the. I think we could have had a conversation about it before that.
Yeah. Yeah, it's interesting. The application of things there.
Yeah. So I'm looking forward to some people, as opposed to the amount of fawning praise that I've heard so far. I'm waiting to hear some people starting to find easy ways to break it.
Yeah.
And certainly easy ways to get, I don't know if you want to call it degenerate behavior, but like and also just to be on the engineering teams in terms of how they try to fix the known problems in ways that you've got to imagine relate to like either fine tuning or other explicit constraints.
Yeah.
I just wonder, because again, the real problem for a lot of these teams is that like this isn't just a research project. There is significant amounts of money on the line here.
Oh yeah. So yeah, I noticed you said that you were catching up on the BICA conference. What did you think about some of the stuff going on there?
Yeah, I mean, terrific stuff, right? I mean, super interesting. I know you've attended before.
Oh yeah.
Right.
Yeah.
Right. And anyway, it's every time I'm listening in, it's an interesting conversation, and it's quite wide ranging, So I really enjoyed it. It's just been so busy here. Yeah. Building out the lab. So we're kind of like on the last like big changes that are needed in the lab space to really flesh out the cell culture facility.
Okay.
And it's down just some things where we've got to like actually shut down the entire building. It's just some of the plumbing work. We're just going to have to turn off the water for the entire building to get it done.
Okay. Yeah,
but this weekend, so I'm going to take off pretty soon. This weekend we're doing a biopunk hackathon.
Okay.
And so we'll be doing all sorts of. I mean, I think there's definitely a few projects that have been proposed with bounties, and but the big thing that we will be doing is James and I will be showing people, if they're interested, how to convert a 3D printer into a 3D bioprinter.
Okay.
So both hacking the firmware and replacing the plastic exterior with a syringe, mechanically controlled syringe. And then you can do what they call fresh bioprinting. So you're printing into a hydrogel. So
That's pretty cool.
it is very cool. James, the team that went to Pittsburgh to learn this, we were all super impressed with what they were doing. So this was like a real tissue engineering group. It's Carnegie Mellon that does this. And like the former student of the PI, who's now a professor at UPitt, is kind of the technical guy who has like so many open source projects. And it's great because they're a tissue engineering group, but they, in addition to the 3D bioprinting, in addition, they're doing soft robotics development to test the tissues that they're fabricating. So when it comes to the heart, they're, again, making kind of mechanical devices to either to be controlled by the muscle that they're making, or to do some sort of test stretching or things like that to the material. They doing this all, for vessels, for skin, for etc., or making bioreactors for, say, some sort of liver-like tissue that they've generated that they just need to maintain in culture for a long time. So I gotta say, we really lucked out in terms of finding this particular group and being able to learn from them these skills is awesome. So trying to bring that to the lab, and the real opening here is that basically there's not a lot of groups that do this with neurons. So there's organoid groups. I was trying to get this across to we had a visitor, had some journalists come through the tower, and we're not trying to do the kind of brain science that, say, Alison Moultrie is doing at UCSD. But we can do something that's still kind of research grade, in terms of how neurons in these biological scaffolds, the connectivity that they form, and the kind of complexity that you can find in terms of complexity in shorter time frames that potentially could be grown, would be kind of one of the metrics. I mean, in addition to the kind of information theoretic metrics that are kind of standard for the electrophys analysis. I think that's, I mean, that's our big thing this weekend. We've got a lot of got a lot more to say about tissue engineering. And
All right. Well, yeah, good luck with all that. I know you've been working on that, like, kind of a long-term thing, and it sounds like it's coming together now. So,
and then at the end of the month, we've got Katerina coming to present.
oh, okay.
Yeah. So she's got this is she's a postdoc at UC Santa Cruz, and her co-founder. So they've got a startup that's, again, focused on some aspect of organoid culture. It's called like Open Culture Systems or something like that. Right. And they're going to be coming to talk about real organoid culture. Yeah. But their work has still primarily been, brain science work, right? So they're trying to grow a brain, trying to culture a particular tissue target, and that tissue target is like, it's supposed to capture that particular real brain area, right? And then be able to understand things about that mechanistically, or relating to cell types or things like that, right? Whereas organoid intelligence is like, you can flip it and use the engineering to generate the kinds of cell types, organization that you want, and that hopefully are simulatable, because then perhaps they can be used in computation in a more directed or controlled fashion. Anyway, that's the goal.
Yeah, great. Well, thanks. All right. So I don't know, did Paul or Vidhi have anything they wanted to add? We'll wrap it up for today. If not,
I've got nothing. At some point, I'd like to know more about Morgan's background, but we don't have to do that during the meeting.
No, I'm just experimental psych and molecular biology.
Okay. Are you a psychiatrist, or because I see?
No, I do. Yeah, no, I do psychiatric research. I mean, but this is like, I do psychiatric nerd. So
Okay.
I do computational modeling of large MRI data sets.
Okay, we should definitely talk sometime, because I'm planning on doing an MD PhD, and
Nice.
there's a good chance I'm going to end up doing psychiatry, either that or neurology.
No, psychiatry is the best. I just brought that up just because there's an interesting program in Austin at the Dell Medical Center. So it's great stuff, and there's the other great thing is there's so many publicly available neuroimaging data sets that you can be working with now and learning from.
Yeah, I have a few pubs using those, so
Okay, cool.
good that they exist.
Yeah.
all right, that's great. All right, so I think that's it for today. Thanks for attending, and if we're interested in doing any features or presenting any or talking about papers, please let me know. And otherwise, see you next week. Thanks. Bye.
Take care.
Bye. See you
Take
next
care.
week.
I'll see you next week. Bye. Thanks.